dokie. How's everybody doing this evening?
Good.
Excellent. Wonderful. Everybody excited for learning and stuff and junk? Hopefully. Everybody kind of just done with it? Done with okay, hands up if you're done with this week already. Yeah, how many midterms did you have today?
One.
Yeah, which one?
Operating with the algorithms one.
Algorithms, operating systems.
On paper.
On paper?
It was
Oh.
on paper. It was bad.
Oh, you guys were spoiled in 2MP3, eh?
Yeah.
Yeah. What are they doing in algorithms right now? You guys?
Single linked list.
Singlet? Really?
Yes.
Yes.
And
We're all-
a search and sort.
We're all the way a month in, and they've only done a thing that we also covered in 2MP3.
They're starting recursion.
We're doing classes though.
They're starting with
Doing everything
Don't worry.
Yeah,
It's the same.
Yeah, it's not like I don't think it's.
They did like C++
though.
first and then.
Like,
Yeah, we're starting with
I don't even know when we get into like big O notation and that kind of stuff.
They haven't even talked it? Okay.
No.
No,
You'll have assignments on that.
Yeah.
When?
Yeah. Well, I think by this week when I was doing 2MP3, we were almost, maybe it was like this week or the week after, we were doing linked lists as well. So I was able to teach you C at the same time as covering as much algorithms material as they've covered, eh? Not to toot my own horn or anything. But no, of course, I'm sure you've been doing lots of stuff in that class, and I'm just funning with you. So, all things being equal, which they're not, but anyway, let's continue on today. So, on the docket for the lecture today, I'd like to finish off the material on I2C, which in and of itself won't take too long. I'd like to do a digression for you guys into shift registers, because I think that's an important thing. I don't have any slides material for it, so it's going to be on the board. But shift registers are a very useful and important concept / device that you should know about if you're going to take this course. How many people know what a shift register is? Yeah, okay, good. Well, we'll cover them then. I might even put the thing up, and we can use the middle of the board this time. So I took a look at the material for Lab 2, seeing as Lab 2 is also going on this week. It seemed like we've actually covered everything for Lab 2 that that's pertinent, that I have material for. The only thing that sort of I don't... LCDs would be one thing that I would give you slides on if I had the slides. But I dug through the archive and there's nothing on them, so, and I hadn't had time to put it together. So we're going to continue on from I2C to real-time clocks, which is going to be a short unit. We'll probably get it over with today. That's going to be relevant to Lab 3. That sound good for everyone? Awesome. Excellent. So let's continue then. So last time we were talking about I2C, communication protocol. Just very, very quickly recap that. So the idea with I2C, you have two lines, you have a data line and a clock line. These could be just general GPIO pins that you've configured in this manner. One of the nice things about I2C is that it's simple enough that you can actually just kind of hack it out in software. But of course, there are going to be dedicated ICs for this as well. But anyway, rough, very broad sketches. You've got the data line, which of course is responsible for the transference of the data, which includes both the information you wish to transmit and addressing information for who you want to send it to. And then we have the clock line, which synchronizes the information in the data line. very, very quickly, the I2C communication protocol is a master-slave communication protocol. So you have one device that is the master that controls such things as the clock, and then you have slave devices, which are the things being addressed. Examples of the master might be something like your microcontroller. Things that are slaves might be things like an external EEPROM chip, or something like a thermal sensor that is also communicating via I2C. So yeah, and last time we focused a fair amount on the particulars of, how these signals are transferred, how, the fact that any one of these devices, be it master or slave, can sort of pull that line down because all of these pins are being configured in open drain. So, and since the line itself has a pull-up resistor, it's high when nothing is pulling on the line, but when anything pulls on the line, it goes low. So the slaves have some ability, for example, to control the clock line. They can hold the clock down while they finish a calculation and then release it, and then it jumps back into its regular transfer rate. Stuff like that. So far, so good? So far, so review. Any questions related to last week's lecture? Don't think so? Okay. I did make a technical mistake, which was pointed out to me. When we were talking about the protocol, when the master device sends out a request to a slave device, and then that slave has to respond to the master, I had told you guys that it just immediately jumps into data packets, which is incorrect. It actually, the master itself also has to be addressed during that response communication. So there is an address section in there. So we're good. So anyway, moving right along. Here we are. So just some notes on clock synchronization. So one of the interesting things about the I2C interface is that it supports multiple masters being connected on the same data bus. However, if that's going to be the case, you need some way of synchronizing the clock signals, right? If these different chips, which both think they're in control of the clock signal, it's like, you can imagine if you had one data line and MCU 1 is writing, something like this, right? And MCU 2 is writing something like this, right? Then effectively, this signal would be, that plus that is equal to low the whole time, which means that no clock will nothing will happen, right? They'll sort of blow out each other's clock signals. And even if these things are slightly offset, you might have something like that, But anyway, so clock synchronization is an important thing to solve if you're going to support multiple things controlling the clock, right? So, this is how it does it. Each master device has a counter. The counter resets if the clock line goes low. When the counter counts down to 0, the master releases the clock line, and thus the clock line goes high. So, essentially, so if we have controller 1, right, and we have controller 2, each one of these will have an internal counter which is counting out how long the low period needs to be. So the clock line will be low if either of those guys are pulling it low. But it synchronizes, it starts counting that out when the when the clock line goes from a high to a low state, so when it has a falling edge, right? So it's like, even if, say, you know, the timer on MCU 1 is equal to 3, and the timer here is equal to 4, right? If we have the falling edge, then, you know, if we have a falling edge, then this guy starts counting, right? He's like 1, 2, 3, or I guess it's 0, 1, 2, 3, and then he releases right here. So he goes rising edge here, right? But he's holding low that whole time. If this guy has 4, then he's holding 1, 2, 3, 4, and then he has a rising edge. If you combine those two signals, what you end up with is that guy, right? Because, again, any one of the devices holding the line low will keep the line low, right? And because this counting always starts on the falling edge, basically, you may have the effect of lengthening the low period in the clock signal, so you'll have like some effect on the frequency perhaps, but you won't run into a synchronization error where, you know, if these guys were just counting, right, and this guy was expecting a period of 3 and this was expecting a period of 4, it wouldn't take long for these two signals to become out of sync, right? And then you're having, you know, the same types of issues that I was pointing to that I erased there. Does that make sense? Everybody following so far? Good. So, when all masters concerned have counted off their low period, the clock line is released and goes high. After going high, all masters start counting their high periods. The master to complete its high period, first master to complete its high period pulls the line low again. So, similarly to this process, the same process happens once we go into a rising edge transition. However, it goes the opposite way this time. Rather than requiring the consensus of all of the master devices in order to allow the line to go high, the first device which pulls the line low wins, essentially. And at that point, you actually do have a low what do they call it? Falling edge. There we go. Cool? Question?
So is the top line like the data line or is it the clock line?
This is the clock line.
Okay.
Yeah, and this is, I should have done it reversed, but this signal plus that signal equals that signal, right? At least with respect to the electronics, right? Make sense?
Yeah.
Good. Any other questions? Yes.
So those are two different clocks on two different devices that are trying to sync up.
Yeah, exactly. So if you imagine two microcontrollers, right? Microcontroller A, clock signal that it's trying to send, right? Microcontroller 2 will have its clock signal that it's trying to send.
And so you were saying timer 3, that's just an example, frequency, and then there's another example frequency to try and sync up over
Yeah.
time.
So this is the mechanism by which multiple master devices can create one clock signal from the two that they keep that might be configured separately, right? Now, just as a side note, obviously if these, even under this scheme, if they're too far, if they're configured too far away from each other, you may still theoretically run into problems, especially if you start running into overflow problems or stuff like that. So, on the counters or on the timers, but, you should try to keep them reasonably close together, but this arbitration mechanism makes so that they don't have to be exact. Yes?
Is there any reason why it works with bitwise addition, or is that just a coincidence?
Excellent observation. Yeah, bitwise, so bitwise and, right? Yeah, it's because we have implemented a hardware and operation. So, just to return to the circuit diagram for a moment, right? Let's say we have MCU 1, MCU 2, right? Let's just do the clock line. And maybe, one slave device or something, whatever. Right? This is what the clock bus, this is what the clock line would look like as it was wired up, right? So, all of these inputs, all of these ports are configured in open drain configuration, right? So, if nothing is being written, these are in a high impedance state, right? So, disconnected, essentially, right? So, if all of these guys are disconnected, what's the voltage on this line? Right? It's 5 volts, right? Because there's nowhere for the current to flow to, right? So, essentially, all of the electrons, the current actually is the inverse of the way that the electrons flow, as I'm sure all of you are aware. But, so the voltage sort of floods across the resistor into this line, right? It stays there because, it's got nowhere to go. And so the voltage across this resistor will equalize very, very quickly, right? Because hypothetically speaking, you don't want much capacitance in this line, right? So because there's no current flow, there's no voltage drop across this resistor, so this line attains 5 volts, right? So what happens if this guy opens up its drain, right? That's the drain, You can imagine a little switch in there, right? So all it can do is open and close that switch. When it closes this switch, current flow is established, right? I wonder if that's a problem. Anyway, this line goes low, right? Because you now have that voltage drop across the resistor. So VR is no longer equal to 0, right? So this line goes low if this switch gets closed, right? So fine. If we have another one, right? Essentially, this guy is the AND of these two switch positions, right? So if this gets closed, then it's low. If both are closed, then it's low. If that one's open and this one's closed, it's low. In the other case, it's high. So that's why it looks like bitwise AND, because it is. Make sense?
Yeah.
Hopefully that was useful to people. Good. So yeah, and then on the edge transitions, they start they restart their counters every time there's an edge transition on the clock line. Yes.
The dotted, like, offset sort of lines on the clock too, what do those represent?
So, let's see here. I imagine in this diagram that would be the position of that waveform if it hadn't been for the synchronization.
Oh, okay. And the arrows represent, like, what triggers what, correct?
Yes.
Okay.
Yeah. So, yes. So how this would work, I'm going to use the monopod anymore, but I'm going to use it to point at stuff. So, clock 1 initiates the low period on the, controller 1 initiates the low period on the clock signal. So SCL goes down at the same time as clock 1. However, it takes a clock cycle for the second one to pick it up, right? Because it's not going to know that instantaneously. It requires a clock. It requires one, at least one clock. What do you call that? Clock period. Clock cycle. Yes, thank you. It requires one clock cycle at least in order to pick up the transition, right? So it's going to start its low period at that point, and then count it out. This guy's also counting out. He might have a shorter time to count, so he lets the line up, but this guy's not done counting, right? When this guy lets it up, then that lets SCL high, which then indicates to this guy, okay, I can start counting as well, because the line has actually gone high at this point. Make sense? Good. Any other questions? Good. Excellent. So, so you have a few working modes with I squared C. The master and the slave can both act as a sender or a receiver. I'm not completely honest why it needs its own slide, because this should be implied from the fact that we've been talking about both masters and slaves sending and receiving stuff. But perhaps it's the particular issue, it's the order in which the operations are here. So, in master-sender mode, the master issues the start address and then transmits the data to the addressed slave device. When it's receiving, it issues start and address and receives the data from the addressed slave device. When the slave is the sender, the master still has to issue the start and the address of the slave to send things, right? So again, slaves are not it's not possible for the slave device to initiate the communication. That must be a master, because the masters are the ones that have control over the clock line, and that's essential, right? So, and then in slave receiver mode, the master still issues the start and address, and the slave receives the data from the master. Again, I think there shouldn't be any questions about this, right? Yes?
So what's the difference between like modes like the master, sender, and slave receiver? Is it just like for like that specific, like for the master and slave, but it's like the same like process?
I can't tell from the description, can you?
I don't know, that's why I'm just confused, just because it's like they're like the same thing, so I'm just making sure.
Yeah. Like to me, it would seem if the master is sending, then the slave is receiving, and if the master is receiving, then the slave is sending. Like it would seem to me that these would be in pairs, you know. But what do I know? I just teach the class. So, yes. So this is where I wanted to bring in the digression on shift registers. So you'll notice that we have these things called shift registers that appear inside of the structure that controls the manner in which data is sent out, right? So it would be useful to know what they actually are. And I think that's relevant and pertinent. So let's screen up. There we go. And there we go. All right. Cool. So with I2C communication, the bits are sent one at a time. You may notice that, unless you are programming in the very extremity of assembly programming, normally you don't deal with individual bits. Normally you deal with integers, collections of bits, because dealing with individual bits is kind of a pain in the ass, and it would take at least 8 times as long to do anything, assuming you're working with 8-bit integers, which nobody is anymore. So it would take at least 32 times as long to do anything if you had to work with the individual bits. So, shift register. A shift register is a collection of individual flip-flops, right, which are arranged in such a manner that data can be loaded into them in parallel, and it can be extracted from them in series. So if we sort of imagine, you know what, I'm only going to do 4. 8 is just too much. So, these things can be configured in many different ways. It's possible to get shift registers that have like one of the different means of access, which I'm about to describe, removed. Some of them only do 2 of them, But I'm going to talk about all 4 ways of putting data in or out of these things, right? So essentially, there are 2 ways in and 2 ways out, right? So you can load data in parallel. So if we imagine for a moment we're working with 4-bit arithmetic, if we had the number 7, for instance, that would be 1, 3, 7. There, right? So you could load the number 7 in here using the parallel access, right? You could also get it out the same way. But the thing that makes this work with I2C communication is that you can also shift the bits down this way, right? So there's a function where if, let's say, like this is going out on the data line or something, right? Is it SDA? I think it's SDA. So it's like send, this one gets put out onto the network, this guy moves here, this guy moves here, this guy moves here, and then, probably a 0 or some undesirable value gets loaded in the backside. This is very similar to the idea of a left shift operation from bitwise arithmetic, right? But the idea is that you can just kind of one by one pump these bits out of the shift register and out over the network. Make sense? Any questions? I realize I'm not doing this at the level of like electronics and, I haven't drawn any resistors or anything. We're basically working with block diagrams, but does that make sense to everybody? Yeah.
Is one method better than the other? like, is sending 4 at once like this, is that better than sending 1 by 1?
Sending 4 at once is like sending data in parallel is almost always better in terms of speed, but when you're doing serial communication, it has to be serial, right? So it depends on the bandwidth that you have available to you, right? Like if you open up a computer and take a look inside, right? You'll notice that like various lines that go, for example, from your hard drive all the way down to your motherboard, those will tend to have a lot, like they're ribbon cables, right? They contain a lot of individual lines. That's parallel communication, right? So that's parallel going out. And essentially this is like maybe not even that useful for parallel communication because you might want more of a buffer than just the one, you know, but maybe one is sufficient. USB, on the other hand, Universal Serial Bus, it's only got the 2 lines in there, right? So this is like, depending on how many cables you have available to you, serial communication is, you know, often preferred. It also will reduce the cost of the cable, which, you know, is generally good. Yes?
So this is useful for I2C because it is a 2-wire interface.
Yeah.
So
Mm-hmm. Yeah, exactly. Yeah, so this is how the data gets loaded and then sent out if you're using like a peripheral. Otherwise, if you're if you're just hacking together an I2C data line in software, you'll basically have to replicate this functionality in software, right? So, like, for example, just in pseudocode, right? You would need something like, you know, while data is, you know, well, probably better to do with a timer. You know, while timer, whatever. Let's say we had like data up here is equal to, you know, 7, 4 or something, whatever. You want to isolate the bit that you want to send, right? So we're sort of, if you're sending in big endian, then you send the biggest stuff first, right? Which is the stuff sort of at that side of the integer. So it would be like, you would say something like, the bit you're trying to send is, you know, data and 8, 0, right? Because 8, or hexadecimal, not, what am I doing? I got the symbols mixed up. Is that right? Am I doing that correct? I think I am. All right. So, you know, if you were to take a look at the actual binary code here, right? Hexadecimal 74 is this binary number, right? So if you perform bitwise AND with 80, that's there, right? So that will always extract the last bit, right? Once that's finished, you can say data is equal to data right shift or left shift by 1, right? So what that does, right shift by 1, it moves this whole thing down by 1. And then backfills with zeros. But we don't care about them, and I want to pick them out visually as being not included in the original data, right? So if you then perform bitwise AND with this same number, you'll get 1, right? Which is this bit, right? So that's how it works. Make sense? Question?
If we can kind of like go back a little bit, what are shift registers like really used for? Like, I'm just like, I feel like we're getting really into like specifically like what it's doing, but if we can like
Yeah, sure.
back a little bit.
So back up to like the macro level. It's for queuing data, right? The problem that the shift register solves is how do you go from, say, a 32-bit integer inside of a program to a sequence of ones and zeros that are sent out sequentially over one data line, right? You need some way of sending them in sequence.
So it's taking like, as you said, like an integer, breaking it down and sending it.
It's, yeah, so this is the part where it breaks it down. Although, this isn't much of a breakdown because, like, whenever you store any number in any register, this is what it looks like at the individual bit level, you know? What's different about this, a shift register as opposed to a regular register, is it's got this built-in feature where it can shift the values down over time so that it can pop out one bit at a time so that those bits can be sent over the network. Does that make sense?
And but it's getting shifted down, like that's, like as you said, that's the difference between like just storing data, it's being now like sent.
So think about it this way, right? The shift register has a request function, right? So when a bit is requested, it'll take the one on the end and then shift things over to fill that place so that the next time a bit is requested, the next bit in the sequence is being requested. Does that make sense?
Yeah.
Getting there?
Kind of. Yeah, kind of.
Question?
So the shift registers basically store the data until we need it, whereas like the data line signal would be like you can't control like requesting when, if that makes sense.
It's more like how do you get the bits that the data data line is transmitting. Does that make sense? Yes?
So like, let's say you had the header that you wanted to send over I2C that was like, let's say the ID was 2, right? So in the header you send the ID that you want.
Mm-hmm.
So you would put 2 in the shift register, and then you would tell it to move 8 times for those 8 bits in the header.
Mm-hmm.
Those would go out on the data line,
Mm-hmm.
and then that way you now have your like code number to a real number through like signals.
Yeah.
Yes?
Yeah, so yeah, it's like, it really, like, the crux of it really is conversion between parallel signaling and serial signaling, right? Like, in order to go from, like, everything inside of the processor is done in parallel, right? Because it has to be that fast, right? So, you know, for your CPU, you got a lot of lines coming out, right? In order to send it via, 2 data lines, this data has to be serialized, right? So it comes into the shift register, right? And pops them out one at a time and puts them into the network. Does that make sense? A little bit? I'm trying to think of a clever metaphor that involves video games.
Okay, I think.
I can't think of one. All right. Yes.
So if you had like unlimited money, you wanted to do it very expensively, for that you could instead just do 8 wires directly connected to your other single MCU that you wanted.
Yeah.
Use the shift register so that you can only use, so that we can use those 2 data lines to represent a lot more and connect to many more devices. Yes? Do you know what I
Run
mean?
that by me one more time.
Like, let's say that you instead of going like this, you just went 8 straight to the other to the
Oh.
peripheral device.
Yeah,
Right? That would be a lot cheaper, or not a lot more expensive and a lot faster.
yes.
But this shift register allows it to just send things out to a bus so
Yes.
that everybody can listen to it and not just the one thing that you're connected to.
Yeah, so yeah, I'll bring that in. So let's say we had like CPU 1 and like CPU 2, right? Yes, if you wanted to, you could come up with a direct connection between these 2 CPUs for like, 32 bits or whatever, right? But that's going to use that many GPIO pins, right? Like you can drive a signal in parallel, absolutely. In fact, if you look at like really old computers from the 90s that have like the printer connector for like I don't know if you guys are too young to even know what I'm talking about here, but you used to have like a connector that would look like this, that would have like 1 million pins in here, and like 3 rows of them, right? And that would be like your printer cable for a computer. Parallel communication. USB has overtaken it because like we're now able to clock things sufficiently fast that parallel communication isn't necessary for these types of applications. But if it was serial communication back in the 90s, you would have to wait a long time for your document to print, for example. But yeah, you can directly connect to CPUs using this. The question remains how to connect other devices to that, and if you wanted to connect some poor EEPROM chip, that poor EEPROM chip would also need 32 bits going through it, right? But yeah, the shift register serializes the data so that it happens over the course of time, rather than all at once. Like if we wanted to send this number through parallel communication, very easy. You just write each pin with the 1 or the 0 corresponding to the value, right? But with serial communication, because you have to add the element of time, you have to compress like the 32 data lines here into 1. And you have to use time to do that, and that's what the shift register does. I have a question over here, I'll come back to you. Yes?
So, for the shift register, like, basically, does it just load however many bits? Here you have 4 bits. It loads 4 bits in, and then send them off one by one.
Mm-hmm.
And then once those 4 have been sent, then you load another 4 in.
Yes.
Is that what it is?
Yeah, that's what we're doing here. Yeah. Question?
Yeah, just 2 shortish questions. First question is, like, the receiver would also have a shift register that they're receiving all the data into, and then loading, like, in parallel back into their...
Yeah. So, yes, very good observation. These things, like you can have data coming in and data going out. And if you're on the receiving side, it's this exact process, but in reverse.
Okay.
Rather than, loading all of it in at once and then sending it out one by one, you receive it one by one and they get shifted over as they're being received. And then when the whole register is complete, you load it out in parallel into one of the registers of the CPU to be executed on, or whatever you want to do with it.
Great. And my second question was just that, like, in I2C, can you have multiple data lines to send information in parallel, or is it, like, just serial?
It is just serial, just one data line. Yeah. Like in theory, these older parallel port configurations would also, like one of the pins in there would be a clock line, and it would be synchronized parallel communication, which is what you're talking about. And by adding one additional data line at this point, you double the amount of information you can send and how quickly. But generally, that's not the issue anymore. Like things have gotten fast enough that serial communication is like very reasonable. Like like consider, each one of these lectures generates about 10 gigabytes worth of data that's being recorded, right? I can download that via a USB connection to my computer in, maybe 8 minutes. Pretty high data transfer rate, right? So that's kind of why parallel communication between peripheral devices has really fallen off in recent years. Question?
Is there a relation between the number of flip-flops in a register and the total size of the packet you send?
There doesn't have to be.
Okay, so you could have just 4 and you're sending 32-bit packets, you just have to reload it a lot faster.
Yeah.
Okay.
In theory, you could do this with 1 bit
Right.
and just reload that bit all the time. Now, 4 is kind of a facetious number, Really, the number that you'd probably be shooting for is 8,
Yeah.
because that's the byte size that's being sent over the network anyway. So you're gonna have to after 8 bytes, you have to wait for the acknowledgement anyway. So it makes sense, right? But yeah, good question. Question.
Yeah, I'm sorry, could you repeat what you said a minute ago about the shift registers, they shifted, but then they all shifted up into the CPU in parallel?
Yeah. So let's just put a 1 in here for the time being. Yeah, you can just read all of these simultaneously, right?
Okay.
So it's like conversion back into a parallel format, right?
So it could be extracted both in series or parallel?
Yes.
Okay.
Some shift registers are restricted in that. Some are specifically parallel to serial. Some are specifically serial to parallel because if it's only ever going to be doing the one function, why have the other ones there? It's just costing you money, right? For no purpose. But yeah, good. My goodness. Any other questions?
Thank you.
Okay, let's see if we can quickly get through the rest of the I2C slides, shall we? There's not too much left. In fact, I think it's just a picture of an EEPROM chip that's left. Good. Yeah. So, EEPROM chip, clock line, data line, voltage source, no, voltage sink, voltage source, I think, yeah, and yeah. This is the communication protocol, which basically this is the same thing we did on the board at the end of the last class. Yeah, I don't know if I need to say anything more about this because we've already covered it in detail. But any questions in general about I2C? Because I think we're moving past this point. Yeah.
So does I2C just mean it's the master and slave kind of style? Is that just all the I2C really means?
No, it's that in combination with this specific the requirements with respect to what the waveforms look like on the two communication lines. I don't know if SPI is also master-slave. Can anybody? It is?
Yeah.
Yeah, okay. So yeah, there are other communication protocols that are master-slave, that have a master-slave sort of setup. There are also communication protocols called daisy chaining. So in daisy chaining, basically you have different devices, right? And the message gets sent, it's received by this guy and then passed along to the next guy, who passes it along to this guy, who passes it along, etc., etc. So it's not like a shared bus protocol, it's like each component in the chain is responsible for passing the signal along if it's not addressed to it specifically. That's like another sort of way of going about it. But yeah, I2C is like, it's more than just master slave. It's also the combination of you know, the clock signal and the data line behavior. Question?
So the fact that both clocks are trying, or both masters are trying to take control of the clock line, implies that they're both trying to send a message across at the same time. But how would they both be able to send across their message across a singular data line? How do they not interface?
Because whichever one pulls the line down first wins arbitration. So we had some slides about arbitration somewhere in here. Yeah, multiple masters. So if they're both masters are also simultaneously checking to make sure that the data line is behaving the way that they have sent their data, right? So the first, so if they detect a mismatch between what they meant to send and what they actually got, that's always going to be, the other guy pulls it low when I expect it to be high, because they can't pull it high, right? So whoever pulls it low first wins arbitration. The other guy will back off until he's finished. Right?
That was not a hard one. PDF started glitching. I don't know why. In the middle of nowhere, finding it.
Yeah, I guess it doesn't really use to.
I don't know. I recall most of it.
Oh, no, it goes into slave mode when it detects the other master.
I do not have as many
It takes control of the clock.
I don't have as many
The master that wins arbitration, it's not that he takes control of the clock, it's like he continues having control of the clock that he had anyway. The other guy backs off and becomes a slave temporarily until he's finished. Yeah.
While I was doing your questions, I was doing my other questions. And by doing those questions, I mean, like afterwards, I look at the questions.
Yeah. Yeah. And it doesn't matter if like up to that point the signals would have been identical anyway, so it's not like it's interfering.
I like how we're talking about this in front of the recording camera, like right behind it.
Yeah, no.
Hey, if you're watching on YouTube, you know, we didn't say anything. Yeah, just ignore it.
We're just talking about an assignment we did.
Yeah.
Where we were totally allowed to collaborate.
Yeah, I should stop recording, but I don't know. Wait, I mean, is he gonna? I don't think so. Like last time, we just like put in the first 3 seconds of like a random record.
Oh, I thought you did the editing.
No.
Almost like one line going in,
There.
one line coming out. So since it's one line, I'd say that's, yeah, it's probably used. Yeah, I don't know that for certain.
I should probably zoom into his face.
I feel like we just get like a perfect 100%.
Hello.
It is possible.
Did you like defer the exam?
I should probably stop recording.